Have you ever stopped to think about how we manage to grow food on such an incredible scale? It turns out it involves solving some truly massive engineering problems, right there in the dirt. Today, we're going to dig into one of the most fundamental of them all, shaping the very land we farm on. And it all kicks off with one enormous question.
Okay, just try to picture this for a second. A single farm field, over 230 acres. That's roughly the size of 150 football fields all stitched together. How in the world do you precisely grade a surface that gigantic to make sure every single drop of water goes exactly where it needs to? Yeah, you can't just eyeball that one. This is where some absolutely incredible technology comes into play. The whole thing is a process called landforming. And really, in simple terms, it's about sculpting the earth with almost surgical precision. The main goal here is to create the perfect slope across these huge areas to control how water moves. And that control is just absolutely critical for growing healthy, abundant crops.
Now, you might be thinking, well, wouldn't the ideal field just be perfectly flat? Like a giant billiard table. But actually, that's not the case at all. The real challenge is all about managing water, and a totally flat field can actually be a complete disaster.
See, if a field has low spots, water just pools up and it can drown the crops. And if it has high spots, the water just runs right off before the soil can absorb it. All of this leads to wasted water, soil erosion, and really patchy, uneven growth. So the bottom line is, getting the shape of the land just right has a direct impact on the food that ends up on all of our plates.
So how do you even begin a project of this scale? Well, you can't move a single scoop of dirt until you know exactly what you're working with. So the very first step is to create this hyper-accurate digital map. Basically, a digital twin of the entire field.
So here's how they do it. First, they set up a stationary GPS base station. Think of it like an anchor, a known, fixed point that never moves. Then, a mobile GPS unit, which they call a rover or sometimes even a drone, systematically covers the entire field, collecting thousands and thousands of elevation points. All of that data then gets crunched by software to build this incredibly detailed 3D model of the ground as it is.
And this is just a perfect illustration of that process. Over on the left, you see the physical GPS gear out there in the field, grabbing that super precise location and elevation data. And then on the right, you see what that raw data turns into inside the computer, this colorful three-dimensional surface map that shows every little bump and dip.
Okay, so once you have that digital twin of the field, this is where the real magic happens. This is the part where engineers and farmers basically get to play a super high-stakes game of SimCity, designing the absolute ideal surface for maximum crop growing efficiency.
And there are really two main ways to go about it. You could do a planar design, which is pretty simple. It just creates one single uniform grade across the whole field, kind of like a giant gentle ramp. But what's really fascinating is the variable slope design. This is a much smarter way to do it that actually works with the natural shape of the land, creating these subtle, complex curves to manage the water while moving the least amount of soil possible.
And this idea really gets to the heart of why that variable slope approach is so brilliant, especially for crops planted in rows. The most important thing, the main thing, is making sure water flows gently down the crop row from one end of the field to the other. What happens side to side, between the rows? Well, that's way less important, just as long as it doesn't create big puddles. This way of thinking lets the design hug the natural terrain, which is just way more efficient.
So the final result of this whole design phase is a map that looks like this, with these smooth, flowing contour lines. You can think of it like a topographic map, but for a world that doesn't exist yet. Each one of those lines represents a very specific target elevation, and altogether they create the blueprint for that perfect surface that's about to be built in the real world. All right, so we have a map of the land as it is, and we have a design for the perfect surface. The next obvious question is, how much dirt do you actually have to move to get from point A to point B?
This is where you hear the terms cut and fill all the time, and it's really pretty straightforward. Cut is just the dirt you need to shave off the high spots, and fill is where you need to dump that dirt to fill in the low spots. The most efficient job, the perfect job, is what they call balanced, where you move as little dirt as possible and you don't have to haul any in or take any away.
And the software, this program here, AgForm 3D, it does this whole calculation instantly. It just compares the original 3D model with the new design model, and it spits out the exact volume of soil that needs to be cut from one place and filled in another. As you can see right there on the screen, it gives you a very precise number.
So for this specific 230-acre field we've been talking about, the total amount of earth that has to be moved is, get this,
Over 42,000 cubic yards. That's a huge number, right? But what does that actually look like?
Well, to put that into perspective, that's enough dirt to fill more than 4,000 standard dump trucks. Seriously, try to imagine that. A line of dump trucks, bumper to bumper, stretching for miles and miles, all filled with dirt from reshaping just one field. That's the mind-boggling scale we're dealing with here.
And that brings us to the final and maybe the most amazing part of this whole process, actually turning that digital blueprint into a physical reality. This is how we go from pixels on a screen to plows in the dirt.
That design file, with all the cut and fill data, is exported from the computer and loaded directly onto the computers inside these massive GPS-guided tractors and earth movers. These machines now know, down to the centimeter, the exact elevation of the ground they're driving on and the exact target elevation they need to hit.
So why on earth do they go through all this trouble? Well, the payoff is just enormous. Farmers use their water way more efficiently, which is absolutely critical in a changing climate. Crop yields go up because every single plant is getting just the right amount of moisture. And since the water flow is controlled, soil erosion is cut down drastically. It's truly a win for the farmer and a win for the environment.
And there you have it. What was once an uneven, inefficient piece of land is completely transformed into a perfectly graded surface. It is a landscape quite literally sculpted by data, all for one reason: to create the best possible conditions for growing our food.
It really makes you think, doesn't it? This kind of high-tech work is happening on farms all over the world, but it's totally unseen by most of us, which kind of brings up a final question to chew on. What other invisible tech is out there right now, fundamentally changing how our food is grown and shaping the future of what ends up on your dinner plate?